Hi guys, sorry I couldn't be there with you today. I had to be away at a conference for chemistry. In my absence, hopefully you'll learn a little bit about the kinetic molecular theory and also how ideal gases um, are different from real gases in terms of their behavior. So starting with kinetic molecular theory. Kinetic molecular theory was published in 1857 by Rudolf Clausius, and it is a theory that describes the motion of molecules in a given substance. And it gives us an understanding of pressure and temperature at the molecular level, where those things come from. So, under the kinetic molecular theory, it states that gases are in constant random motion. The volume of the molecules is negligible compared to the volume of the container. So basically, the gas molecules themselves don't take up very much space. There's no attractive or repulsive forces between the molecules. Again, this is assuming our ideal gas situation. And the collisions between the molecules are perfectly elastic. So when each molecule runs into each other, they completely bounce off each other in an elastic way, and there's a complete transfer of energy. And the average kinetic energy is proportional to the absolute temperature of the molecules, meaning that the average kinetic energy is the same as the temperature. So absolute temperature of a gas. So this would be our Kelvin scale, meaning that there's no negative temperature. With the absolute temperature scale in Kelvin, when we approach 0 degrees Kelvin, the molecules of gas, or the molecules of the substance, will stop moving. So absolute temperature of a gas is a measure of the average kinetic energy of the gas molecules. Molecular motion increases with increasing temperature. So by measuring the kinetic energy, we're measuring the temperature. Molecules in a gas sample have an average kinetic energy, and therefore they have an average speed. Each molecule in a gas has its own speed, but as we look at the gases collectively, they have an average speed. So the individual molecules themselves, they vary from the average speed, but when we take them collectively as a whole, that is the speed that we're going to take as the average. And it's also known as the root mean squared velocity, RMS. Distribution of molecular speed for nitrogen gas at 0 and 100 degrees Celsius, and you can see this line here represents the average speed for the molecules at 0 degrees, and here's the average speed at 100 degrees. So what do you notice? As we increase temperature, we increase the average speed of those molecules. So as temperature increases, so does the average speed for a given set of molecules. So application of gas laws, so the effective volume increase at constant temperature on an average molecular speed. So the volume of the container, that effect of it is going to increase at a constant temperature for the average molecular speed, and that is derived from Boyle's law. At a constant volume, temperature increased the average molecular speed. That is based on Charles' law. So a fusion is the escape of gas molecules through a tiny hole in evacuated space. It used to be that you had to do a whole bunch of calculations with the fusion, and that actually has been eliminated from the AP, so hooray for you guys. Diffusion is the spread of a substance throughout a space or throughout another substance. Those of you who have taken bio or AP bio probably did a lot with diffusion. But diffusion is talking about molecules moving from an area of high concentration to an area of low concentration and spreading out throughout the space. So the average kinetic energy of any collection of gas molecules is equal to 1/2 mv squared at a given temperature. lighter particles and heavier particles will have the same average kinetic energy. However, lighter particles will have a higher average speed. So the lighter the particle, the faster the speed. So how is the average speed of nitrogen gas changed by an increase in temperature? So if we increase temperature, what do you think happens to the average speed? Yep, it would increase. If we increase the volume on the gas, how would that impact the average speed? Mixing with a sample of argon at the same temperature, what would that do? So adding the argon would add increasing moles of gas. What do you think that would do? We'll talk about that when I get back. Real gases. So throughout class so far, we've been talking about behaviors of ideal gases. So we've ignored things like intermolecular forces, so attraction between molecules. We have ignored the volume of molecules that are within our sample. But with real gases, you can't ignore those things. So if we take a look at the graph below, high pressure causes deviation from ideal behavior. So ideal gases will behave at 1. Okay, ideal. And so if we take a look at these different gases at different pressures, you can see that the different pressures causes them, each of these gases, to deviate from the ideal trend of 1. Temperature also affects ideal behavior. So what is the trend? If we take a look here, what do you notice? So the green line represents 200 Kelvin, red line 500 Kelvin, and blue line 1000 Kelvin. So what happens to the behavior of a gas as we increase the temperature? Does it become more deviated from the trend or less? So if we look here, you can see that the lower the temperature, the more those molecules deviate from the ideal. And the reason for that is when we decrease the temperature, we decrease the kinetic energy of the molecules. And by having less kinetic energy, the molecules are less able to overcome the intermolecular forces or the attraction between the molecules, and therefore their behavior deviates from the ideal behavior. So ideal gas molecules are assumed to occupy no space and have no attractions for one another. However, real molecules have a finite volume and do attract to one another. As pressure increases, molecules are forced to be closer together, increasing the effect of the attractive forces. This causes a decrease in the force with which the molecules will hit the wall, which means there would be a decrease in the pressure on the container. Decreasing temperature takes away the energy needed for a gas molecule to overcome their mutually attractive forces. And again, because we're going to have more attraction between the molecules, we'll have less collisions against the walls of the container.